So this morning, what I want to be talking about is an incredibly advanced model. And as a dentist, this is a very basic paper on this topic, and it's talking about the latest in AI. And this is the latest, most advanced application I've seen of the technology in the dental field. It relates specifically to crown design. Obviously, doing something like designing a crown is very formulaic and is the kind of thing that can be understood by a sufficiently advanced model that's trained on enough information. That's exactly what has been happening lately. SoCAD just came out with one. Three Shapes had one for a long time, and there's several other companies on the market that are doing this kind of thing. So how do they work and what's coming up next? Why is this so important? Is the design is what makes or breaks a lot of technology. If you're 3D printing in the office, if you're a lab, takes a long time to do this design step. And especially in the office, every minute counts. So if you can save even 10 minutes with a design process, that's huge. Designers really are the limiting factors. You're going to get inconsistent results. It's very hard to train people. It's just the nature of the industry. Price is fairly low for a single crown. So how can you make this go faster and get consistent quality results? And that is where this technology starts to come in. But what are people doing? What are previous approaches? A lot of these approaches are still used today. They're still incredibly useful, but the basic idea is to use a convolutional neural network. And this convolution can slide around and look at different feature regions and make a heat map and get a lot of information. But you can't easily be able to use logic or see an entire 3D structure all at the same time. And you can't easily generate interdependencies between different feature regions. And that is where these newer models start to come in. But you can do a lot of things. If you look at what happened to basic models, like Pearl, Overjet was able to create one model that used essentially a convolutional neural network, an older image recognition model, and Pearl was able to just take it and essentially do the same thing. It does benefit to have a little more ingenuity in your processes. A lot of the older ones like Sirona were very effective, but they used almost an algorithmic way of generating this. And a lot of other approaches like Three Shape use a hybrid approach where they're using a subtractive method of the surrounding structures to still generate a kind of shape that is functional, that works. So they're supplementing the generative approaches, which can work very well as well and can be done quite quickly. So the idea is these transformer architectures. These are extremely advanced. ChatGPT, that's what the T stands for. Yeah, computationally heavy, but the idea is that they have the potential to understand how different types of points relate to each other. They can have a very large context window. So they can, in theory, create a crown that's harmonic to a very large area in a fundamentally different way than it's created before. Again, they can consider and simply see things differently. So when they generate a crown, it's based on a plan. And they can perhaps generate finer details and, in theory, do a better job than what we have right now. Now, this is what the neural network that would design a crown would look like. And it's incredibly complicated. And even within that, there's levels of increased complexity. But the basic fundamental idea is that you are feeding your information, your mesh, which is then converted to a point cloud, into a transformer model. And first, it goes through a convolutional neural network, a point-to-mesh completion network, which does a couple of things. It sees broader features because you couldn't run 10,000 or 20,000 points through a transformer model. It's just simply too many. So they have an ability to see broader features, which for us would be cusps or neighboring teeth, marginals, or stuff like that. It probably sees it differently, but that is essentially what it's doing. So it's breaking this down into larger feature regions. And then it's using a transformer model using a dynamic amount of questions. So it can essentially ask questions continuously. Where would this point go? Where would be the best feature region? And it can spit out a potential point. for this, which is then used to generate a crown. Like ChatGPT generates the next piece of text based on what it's already seen. This is essentially what it's doing, where instead of spitting out text, it's spitting out points on a point cloud. And then there's additional testing where it's able to then retake that point cloud or many different at the same time and gradually improving until you have a mesh at the very end. And that's an incredibly high level, very simplified, and probably fairly inaccurate way of how these systems actually work. But really what it comes down to is, what does it actually see? What is the input? And it's all based on a 3D point cloud. And this is the same thing you would get from doing an intraoral scan. It's just generating, it's not generating a mesh, it's generating a point cloud. And you're also going to see neighboring teeth. This is all the sort of data that are continually fed into it. The same thing you would get from a single tooth scan. That's all this is, a margin line. It also adds. And of course, there's going to be, in this case, it was trained on a source of truth, which is the final crown. And it did the first step is to figure out what's going on. You know, all it sees is a point cloud, and it's able to use some incredibly advanced processes. This is called a dynamic graph convolutional neural network. And what this does is continually and stepwise create, instead of individual points, essentially individual shape or commonalities. So again, we can understand that as cusps or similar local features, which greatly simplifies the amount of work that we have to do later, because we're just dealing with less points and less features. So the idea is this makes it more manageable down the road. Now, the transformers are incredibly sophisticated. So you have an encoder which uses those, and it's able to ask the types of questions or queries that can then be used. The decoder actually spits out the answer. And this allows us to look at global context. You essentially can ask many different questions of the type of point cloud. And it's really quite an incredible thing on how these fundamentally work. Obviously, it's much, much more complicated than that. There's millions, I'm not sure how many parameters this model used, but it was very many. And finally, those queries, those questions it asks upon those are not fixed. They do continue to change. This is going through many different cycles. And the multi-layer perceptron is essentially data bank, which can be thought of as almost a pinball machine, where the bits of data or their matrices are able to change their values and spit out a new vector, a new direction. And that's all based on previous training data, which are baked into the multi-layer perceptron and other areas. These are able to, by adapting the query and continually adapting them, it's able to start to, in essence, use previous data, previous experience to start to predict, hey, what feature are we looking for and where would that feature likely go? There's a lot of other strategies too, where they try to not only have a limited data set. The problem with this was getting good data. They used various options where they added noise to the crowns just to try to increase the amount of learning. If you only train it on just a few, it'll essentially just memorize what those crowns are. And when you give it something new, it'll give you something crazy. So that is really the problem. So they use various tricks to try to increase and stretch out and thin out the amount of data they actually have. And ultimately, that's the study. And that's probably why somebody like Three Shape, which has millions and millions of crowns to train on, are the market leader and will probably stay on top, because they simply have more data than anybody else right now, except maybe exocad. And the idea is, once you have these points, it's a simple matter, at least conceptually, to start to turn these points back into a mesh. And that's done with a few. Fundamentally, it's very similar to how something like Three Shape would do a scanner. It runs some calculations to figure out the best shape fit. What's the normal, what's the inside and what's the outside, where these points line up, and algorithms, which is the marching cube algorithm. And this is what creates that triangular substructure that you'd see in an STL based on a point cloud. Again, the same sort of thing you might see Three Shape do beneath the hood. This is essentially what they did. Is if they got too far away from the ground truth, if the margin line was off, Again, if the average surface was different, the model gets penalized, and that is all part of the training data. This model really tried to zero in on creating a margin line. I kind of foot stomped this because they used a dyed model, a ditched and dyed scan model with a perfect margin. But reality is this 3 Shape is able to deal with or sees models that aren't ditched and dyed. They're almost invisible. The margin is basically invisible. On an SDL that doesn't have any color, you really can't see a color change at all. So you really don't have a lot to go by. So I really question how well this sort of data, again, this was just academic, but how well this type of approach is even going to stand up to real world problems. And very low training cases, only 388, can't blame them. And they validated it, used a few test cases. They'll divide up the training cases up into different batches and test how well this types of things work. And again, they try to stretch the model. They move things around, shake it, twist it, rotate it. And this all seems to shake up the model, increase the robustness, because now all of a sudden, instead of having 300 something training cases, you essentially have much more. Now, what's really interesting about this study is it was all open source. So the limiting factor on this incredibly advanced transformer model was not actually making the model, because they didn't actually do any of the programming. They surely did some scripting and put everything together, but they didn't actually make the model. It was open source and something that anyone could download and make a weekend project out of. Really, what it came down to is the data and also the knowledge of how to do it. But really, the data and putting everything together is what took the longest. So these types of models are relatively easy to do. Again, if you have the knowledge, you don't actually have to build these types of things from scratch, which I think is very interesting in the dental space, because we have so many needs for things to be trained. And it really, the limiting factor is the data that you actually have. And this worked, this approach, this essentially off-the-shelf approach, this open source, which many things in AI are open source. You can build something like DeepSeek was essentially an open source, used open source components to actually build it, was incredibly accurate. It had a very low mean squared error. The Manhattan distance was a little different than the Euclidean as expected, but incredibly close to the source of truth. But almost, in my mind, this is too close, because natural teeth have even more variation than what we're seeing here. So what this tells me is it could have memorized the data to a degree. And how well did it do? It was a trained model, so it did seem to do quite well. Where it was able to, these processes, it was highly tuned, had presumably an excellent data set, very clean data, and I'm sure expertly trained, and it seemed to do very well compared to other types of models or the untrained models. So the result is that they really perfectly overlap everything. And again, very close. Error was very minimum, as you'd expect, because this isn't necessarily a real world scenario. Different types of tooth types did better, and get an idea of how much data you actually need to train these types of things. Obviously, larger teeth like molars consistently have errors with grooves. There's almost a randomness and an art to making these. And when you look at fit, they did find that these fit quite well. And the interesting thing is these didn't necessarily use the more traditional methods where you're using a subtractive technique where you maybe build up the top of the crown generatively and then subtract it on to a virtual digital die. This works a little different. This creates the whole thing, and it works fairly well. They claimed they had fairly small overlap, which is really very impressive given the amount of data they were able to actually put in and the limited customization they really did on these models. And of course, they are worried about perhaps you're muting out details or oversimplifying some of these tooth shapes. Is that a big issue? That's difficult to say. A contact point precision. And of course, there's a lot more considerations you could bake into these, where when you look at occlusal functionality, the idea of how teeth actually move. That wasn't necessarily included. These were essentially just stamp cusps, which, assuming that's how it's going to go, and it's also going to base it on the source of truth. So it's not necessarily looking at how an ideal occlusion would work or how that would actually work in motion. There's a lot of problems that we do sometimes see, especially from Three Shape, where the contacts are actually concave. Some of that could be the designer. And there's little finer points where, depending on the path of draw, that could start to tip it into the truth. And I'm not convinced this type of model or even similar models are designed to accommodate that. I know Saronis is notorious for giving you a crown that actually doesn't seat. Future improvements, there's a lot of other science is continually evolving data science. It's pretty incredible. One idea is diffusion models, which are found more commonly in image generation, where you could essentially denoise an image of a tooth and then begin with, say, an intaglio surface of a crown, and then begin to denoise the rest of it and create the rest of it around that. That uses crown. That's been incredibly effective in other techniques. So that could be an option. They talked about various ways to simplify. These point clouds are incredibly complicated. Same with meshes. It's just difficult for computers to deal with. But if you were able to convert that into a predictable shape, and they talked about using harmonics to actually do that, and then you could create a shape, which you could then use something like a Fourier transform. So you're essentially converting that into a frequency plane. And the advantage to that is then you could just instantly put it in a matrix, which AI loves, or is fundamental to how it works. And you could certainly improve how you actually train these. The algorithms specific to them could get very sophisticated, and then you'll just continue to get better and better results here. The idea is, although Three Shape certainly is the market leader, there is probably going to be continued room for improvement, and we love to see work on this, because it's highly possible that a model that is very effective at, say, crown design, especially if it's open source, could be used for something you couldn't even imagine. Obviously, not only is it going to save time, it's going to make it consistent. And it could also be used, I should add, to not just do crowns, where potentially something that's incredibly time consuming, like a denture or an all-NX hybrid, could be done very quickly, or a full mouth smile design, stuff like that could become much more efficient. So again, the fact that they're using more advanced models, and more than just using them, but those models are open source. They're available to anyone with the knowledge and the compute and whatnot, and also the data, is very exciting. Hopefully we'll start to see applications that really make dentistry better as a whole. So either way, that's the end of my presentation. Let me know if there's any questions. All right, talk to you soon.